Welcome back. We're in Chapter 16 on nuclear radiation. In this section, we're going to talk about what's actually happening when these big molecules are emitting radiation in order to become stable. So let's look at, again, this idea of radioactive decay is sending out either alpha particles, which are helium nuclei, or high-speed electrons, or the opposite of high-speed electrons, which are positive, or gamma radiation. Okay, so if you want to find out what's happening, you need to know what happens when a particle is emitted. And really what you're looking at is, what kind of a particle is it? What is its atomic number? What is its mass number? And then you're going to subtract the atomic number and mass number from the original, and you'll find out what you ended up with. So big molecules, big atoms, as it's radioactive, will break apart into smaller atoms little by little by little. And every time that a particle is reduced, you have to subtract the protons and subtract the neutrons from the original to find out what you have now. Because as soon as a uranium atom, for instance, emits even one particle, it's no longer uranium. It's something smaller. And then it, in turn, is going to emit something, and it becomes smaller and smaller and smaller. So you have to know what you have, what kind of particles coming off, and then you'll know what you're ending up with at the end. Okay, so actually not that hard in terms of a concept. It's just weird because you're dealing with stuff you've never seen before, usually. Okay, so if you remember, alpha is it's got a 4 in terms of its 4 mass number. 2 is its atomic number. In beta decay, where you're having beta particles is an electron, so it's a -1 charge, but it doesn't really have a mass number. And then positron is a positive charge, and then gamma doesn't have any mass at all. Okay, so just remember that whatever you start with, you're going to have the same amount of mass number and the same amount of atomic number at the beginning and the end. Okay, so in this case, uranium has 238 in terms of its mass number, so the two things that it breaks apart into still has to have 238. Its atomic number is 92, so at the end, the combination between the two atomic numbers still has to be 92. So really, this is a first grade math problem. All you're doing is subtracting the mass number and the atomic number from whatever you've subtracted from the particle. So in alpha decay, you remember an alpha is a helium nucleus, so it's 2 protons and 4 in its mass number, which is protons plus neutrons. So you have to subtract both of these from whatever you start with to know what you have. So here's an example. Radon, which is 86 protons, 222 is its mass number, so that's protons plus neutrons. As it breaks apart in alpha decay, alpha, remember, is a helium nucleus, so it is +2 is its 2 is its protons, 4 is its mass number, it's protons plus neutrons. So you're going to have to subtract these numbers, 22, 222 and 4, and 86 and 2, to find out what your new element is that radon turns into. Because as soon as it emits this, it's no longer radium. It's no longer radon. It's something less than radon. It's a smaller element than radon. So you take 222, subtract 4 from it. That's 218. That's its new mass number. I still don't know what this thing is yet, but its mass number is 218. And then going to its atomic number, it's 86. The alpha particle has 2 of those, so you're going to have to subtract 86. So 86 minus 2 is 84. That's polonium. So 84 is polonium, and you go back and put the 218 that you figured out before, and your answer then is going to be polonium 218. So when radon 222 disintegrates by alpha radiation, it immediately becomes a different element. It becomes polonium 218. That's alpha radiation. Beta radiation is the same concept, but you're not emitting an alpha beam, you're emitting an electron. So you have to take care to make sure that the charges are taken care of. Okay, so you're going to have first its mass number. Now there's no mass number here in a beta particle, so it's 42 divided by minus 0, so it's still going to be 42. You are going to have to take care of its atomic number in a beta particle. You do have a negative atomic number here, so you're going to have to say 19 minus a minus 1, which means that it's actually going to go up. When a beta particle is emitted, the atom gets bigger. It doesn't break apart. It actually somehow reconfigures to get a little bit bigger. So it's crazy. This stuff is awesome. So you would say 19 minus a minus 1. That means that you no longer have potassium. You have calcium. Okay, so you end up with calcium. So when potassium breaks apart by beta emission, it's going to emit a beta particle and then end up being bigger than it was before. It turns from potassium into calcium. Now, since a beta particle has no mass number, these stay the same, but it goes up by 1 atomic number. That's beta emission. Positron emission is exactly the same, only instead of a negative 1, you have a positive 1, which means you're subtracting that positive 1 and it'll go down 1. So manganese stays the same here in the mass number, but its atomic number drops by 1. So if manganese 49 sends out a positron emission, it's going to drop down 1 element to chromium, and it'll still be chromium 49 rather than manganese 49. Gamma radiation is easy because you're not subtracting anything. There's no mass, there's no atomic number, so what's actually happening is that it just stays the same. You have tectinium, in this case 99, is still going to be tectinium, but it's losing some of its energy. That's all it is. The energy that was stored in the nucleus is lessened in an attempt to stabilize it. And in just one last thing, in order to make these radioisotopes, and in things like nuclear bombs and all kinds of really dangerous things, you are making these isotopes by bombarding small particles with a stable ion. So if you have a nucleus of a stable isotope and you bombard it with some particle, say in this case is an alpha particle, you can make a new nucleus, okay? And then that nucleus is unstable and will start emitting things. So right now in the doctor's office, there's all kinds of different radioactive isotopes that they use in diagnostic procedures that have to be made somewhere in a factory, and they make these actually by bombarding one nucleus with another particle or something and making it temporarily radioactive. Okay, so I hope this helps you, and I'll see you in class.